Hi, and welcome to the third presentation of the video streaming session. My name is Vivek, and today I'll talk about our study, Too Late for Playback, where we estimate video stream quality in rural and urban contexts. With COVID-19 pandemic, the assessment of quality of experience, or QoE, for applications delivered over mobile broadband has become urgent as work from home and online schooling protocols increase the demand for video streaming applications. Consequently, communities without access to usable, high-speed broadband, such as many rural communities, are particularly disadvantaged. More than 60 million people reside in rural regions in the US. Cellular deployment, however, is often guided by economic demand, concentrating deployment in urban areas and leaving economically marginalized and sparsely populated areas underserved. And we've seen that there is a lack of accessible measurement datasets that are not only comprehensive, but also representative and inclusive of rural demographics. However, evaluating video stream quality in rural areas presents severe scalability challenges. For one, gathering QoE measurements are time and resource intensive for each network provider. Now let's take a closer look at the scalability challenge. In any mobile or war-driving style campaign, such as ours, QoE measurements typically need applications to run for a minimum duration to aggregate adequate data points for analysis. Quality of service, or QoS measurements, however, take considerably less time and resources to gather. For instance, the graph shown on the top right depicts two different experiments being run on the same mobile device at different times. First, we collect the target QoS metrics. In this case, it's RSRP and throughput. We'll talk about it in a bit. And in the second experiment, we collect QoE measurements from YouTube. For all the three plots shown here, that is CPU load, memory utilization, and system temperature, QoS measurements incur significantly less resources than QoE measurements, which is why, through this study, we explore a methodology that uses QoS measurements to accurately predict QoE. In addition, the QoS measurements can be readily acquired without the use of complex systems. Now we formulate the research question as follows. Can we infer the quality of experience for video streaming applications over LTE networks at scale? And if so, how? To do so, we undertook an extensive measurement campaign to collect 16 datasets comprising of network traces from southwestern US for four major telecom operators, AT&T, Sprint, T-Mobile, and Verizon. Our datasets vary along two primary axes, population density and network load. To obtain data from varied population densities, we collected network measurements within multiple rural and urban communities. For variable network load, we collected traces from crowded events in urban locations that resulted in atypical high volumes of network utilization and, as a result, congestion. We also collected traces from the same urban locations during typical operating conditions as a baseline. Overall, our dataset contains over 32 million LTE packets. For this study, we collect two QoS metrics synchronously, RSRP and throughput. RSRP, or reference signal received power, is the linear average over the power contributions of the resource elements of the reference signals within the frequency bandwidth. For throughput, we fetch a 500 megabyte file from a cloud instance. In addition, we collect video resolution, resolution switching, and rebuffering events while streaming YouTube videos. Next, we set out to model the network performance in order to infer two target metrics, rebuffering events and resolution switching. The models were fed synchronous RSRP and throughput values as input features. After varying the resolution of past samples for the input features, we found that using a sequence of 3 throughput and RSRP values enabled us to strike a balance between model complexity and accuracy. We thoroughly evaluate this for 15 models, including a mix of simpler and complex algorithms. Results are shown in the plots at the bottom. X-axis represents the locations, and Y-axis shows the magnitude for accuracy, precision, and recall. Our investigation reveals that simpler ensemble learning methods such as boosting and random forest perform comparably well with larger, complex architectures such as recurrent neural networks, with at least 85% precision and recall in inferring rebuffering events, and about 80% precision and recall when it comes to predicting resolution switching. When RNNs have marginally higher accuracies, the training times are magnitudes higher than simpler models, such as boosting. Consequently, we select boosting as our optimal model for QoE prediction. Next, we wanted to examine the scalability of our models for different video genres. To evaluate that, we collect over 108 video sessions from 7 different video genres on YouTube. These videos were chosen based on the top trending charts on the day of testing. We collect this in our research facility here at UCSB. Now I'd like to draw your attention to the plot shown on the bottom right. X-axis represents various video genres, while Y-axis shows the accuracy, precision, and recall values. When we deploy a boosting model over these video sessions, we were able to validate the generalizability of the model with about 1.5% deviation from our previous results in the case of rebuffering events, and less than 3% difference in resolution switching. Finally, for analyzing the feature importance of our input metrics, we undertake an ablation study where we measure the performance of boosting using just throughput values, and then with a combination of RSRP and throughput values. The figure on the top right shows the result of this ablation study. We note that the median accuracy gain is about 10% with a maximum gain difference of over 18% in certain cases. The ablation study is useful to learn about the contribution of each input features. And with that, I'd like to conclude this presentation. I'd now like to take any questions, comments, or suggestions from the audience. Thank you.